I will talk now about this sequential optimality conditions. So this is the definition. So we say that feasible point x star. One moment, I lost my pen. Do you see? Oh, okay. Easy enough. Okay, so we say that feasible point x star is an approximate KKT point if there exists this sequence that fulfill this condition, as we already proved. So what we proved, that every local solution of the problem is an approximate KKT point. Every local solution is an approximate KKT point. So, but we can call approximate KKT point any other feasible point that fulfills this property. Okay, so this is when this property holds, you know that this is a good candidate for a local solution. Okay, so because every local solution is an approximate KKT point. So, but what I want to do now is to check this condition in practice. So the idea is that I built an algorithm that generates this sequence xk, conversion to x star, and the algorithm generates these approximations for the Lagrangian multipliers, okay, lambda k and mu k. And I want to check if this approximate KKT condition is fulfilled. Okay, so at each iteration k, I have these values, so I may check if this gradient is small enough. If this is small enough, okay, maybe I should stop my algorithm. I'm sufficiently close to a solution. Okay, this is the idea. These sequential optimality conditions, they generate the approximate KKT condition is one of them, but the idea is that they generate stopping criteria for iterative solvers. So I could do this in principle. The difficult here is this. I should be able to know which are the active constraints at the solution. I don't have the solution, and the active constraints may be different, very near if xk is very close to the solution, but the active constraint must be different. So I must be able to check this without knowing the exact set of active constraints. So this is the active set of constraints. Okay, so we can prove this theorem that characterize an AKKT point with this condition. I can state here the precise epsilon that I can measure this. So this previous condition is equivalent to the existence of the same sequences, and now an additional positive sequence epsilon k, such that epsilon k goes to 0. Now the feasibility is replaced by this, since I don't have now the assumption that x star is feasible. What I have here is that at xk, the norm of age of xk is smaller than epsilon k, and this measure of feasibility of g, of xk and g, is smaller than this epsilon k. So since I'm assuming that this epsilon k is going to 0, this is equivalent to saying that x star is feasible. So you can replace this condition by this, and this you can check in practice. So you check if your xk is sufficiently feasible or close to the feasible set by measuring something like this. You can use your approximation for the Lagrangian multipliers and plug it into the gradient of the Lagrangian. And here you can add every approximation that you get. Some of them will be 0, some of them will not be 0. and this should be smaller than epsilon k. And this is one possible way of measuring complementarity. If Gj of xk is sufficiently feasible, okay, so if sufficiently less than 0, so if Gj of xk is less than minus epsilon k, then the multiplier should be 0. Okay, so this is equivalent to the previous condition. Okay, so there's a proof here. I won't follow it in details, but you can simply check that if you define this value of epsilon k, that measures the infeasibility, measures the optimality, and measures the complementarity, the AKKT condition holds. You can see that these limits are fulfilled, and the other way around is equally easy. So the idea is that an algorithm will generate these sequences, and you will use this condition to stop the algorithm. So to stop the algorithm, you should choose this value epsilon k. So there is a value epsilon k associated to feasibility. You can choose, for example, 10 to the minus 8. So if this feasibility is sufficiently small, it's smaller than 10 to the minus 8, and the optimality also is smaller than some constant, and the complementarity, then you can safely stop the execution of your algorithm. Okay, so this is what is done in practice, and this theory of approximate KKT sequence, it justifies it. It explains why we can do this in practice and why this is a good idea. Okay, there is this theory behind that supports this idea of taking this kind of stopping criteria. Okay. So some examples of algorithms that generate this sequence. So the Augmented Lagrangian that we will talk about in the last lecture. It was motivated by studying this algorithm. It's what it is implemented in our solver, the AlgenCAN, from Projeto Tango in Brazil, in Campinas and São Paulo. So we studied a lot this Augmented Lagrangian method, and we came up with this optimality condition. But we can prove that an interior point method also generates this kind of sequence. So in particular, this algorithm by Chen and Goldfarb, we had studied it. The inexact restoration method, I will also mention it later, but it also generates this kind of sequence. And SQP methods, some classes of SQP methods, sequential quadratic programming, it also generates this kind of sequence. So, I think that many other good algorithms will generate sequence like this. Okay, so usually, when you present an algorithm, a new algorithm, you have to prove that it is converging to a KKT point under reasonable assumptions. So, or at least limit points are KKT. So, with this idea, if you know that your algorithm generates an approximate KKT sequence, this comes for free. Okay, so let me draw here. Note that when we prove the KKT conditions, in fact, what we prove that if you have an AKKT point plus linear independence constraint qualification, or in fact, you can replace it by Mangasyan and Fromovitz, you have a KKT point. Remember, we never used that this point X star was a local solution. we only used that it was an approximate KKT point. Okay, so what we have proved is this. So, and what we know before by the KKT, the approximate KKT theorem is that if you have a local solution, this must be an approximate KKT point. So, if your algorithm generates approximate KKT sequences, okay, so when you assume a condition of this type, you are sure that your algorithm will generate a KKT point. Okay, so and another important thing here is the following. If I can prove this theorem here with any other condition here, I in fact prove that local solution plus this other condition, this implies the KKT. Okay, you simply follow here. If you add local solution and this, you have this, this and this, you have KKT. Okay, so we have used this strategy here to look at this proof that I just showed you, and we looked, well, can we prove this with weaker conditions? And this gives the KKT theorem for weaker conditions. And this also gives convergence proofs for approximate KKT, for algorithms that generates approximate KKT sequence under these weak conditions. Okay, so this idea is very interesting. And these are some examples that we have. So, but I want to mention a broader class of sequential optimality conditions. I did my PhD studying these conditions. So we say that point X star satisfies a sequential optimality condition, and this condition is associated to a mathematical proposition, P, if you are able to find a sequence xk convergent to X star with some property. Okay, it's the property in the approximate KKT sequence is the existence of this other sequence with these other properties. And usually this mathematical proposition P is associated to a parameter epsilon k that goes to 0 when xk goes to X star. And this usually gives you stopping criteria for algorithms. So an important thing about sequential optimality conditions is that it must hold without any additional assumption. You usually don't have a constraint qualification to show that this condition holds. But if you add a suitable constraint qualification, a point that fulfills this sequential optimality condition is a KKT point.
Just one quick question about constraint qualifications. In practice, how do you do with them? Is just you check them ex post for the limit points you are generating, or there is some way you can try to check them in advance whether your procedure will work and satisfy them?
The idea here is that in practice, what is done, the constraint qualification is ignored. Okay, so you run your algorithm and you see, well, is it working or is it not working? So constraint qualification are never checked in practice. And this idea shows that, in fact, you can do this because you have an approximate KKT optimality condition. This holds without constraint qualification. So it's okay if you never check constraint qualifications. But, well, if you want to if your algorithm is not based on this theory, you want to know if it generates a limit point that it's a KKT point, you have to check it in advance. No solver will check it. Maybe it will fail. It will say, well, it didn't work. But if you want to make sure, you have to check the condition by yourself. You have to make the calculation, compute the gradients, and you prove, well, the gradients are always linearly independent for every feasible point. Okay, so at the solution, this linear independence condition should hold. Okay.
And there is no way I can check it a posteriori once I have a sequence that seems to be converging to something. I can check it locally instead of for the whole problem, I guess.
Yes, you can do it a posteriori, yeah. Okay. Okay, so there is this other definition of this other type of sequential optimality condition. This is called the approximate gradient projection condition. So this condition says that there exists a sequence xk converging to x star such that this condition holds. So we have the gradient of the function evaluated at xk, you subtract it from xk, and you project it on this set tk. Okay, so and when you compute this, this should go to zero. This should go to zero. So note that this condition is also associated to a parameter epsilon k that goes to zero. It's this term here. And this set tk that you are projecting is simply the linearization of the constraints. Okay, so here I'm simplifying, to define this, I'm simplifying the feasible set to only have equality constraints. So this idea came from this algorithm of inexact restoration. The idea is that the algorithm has, each iteration of the algorithm has two phases. The first phase, you try to improve feasibility without looking much at the optimality, the function, the objective function. So the first step, you get a point more feasible. In the second step, in the same iteration, you want to improve the objective function, but without losing much of the feasibility that you have obtained. So this is why we have to minimize at this tangent set here. So the point z such that this holds, this gradient is zero, are the points that if you approximate in first order, you don't lose feasibility. Okay, so you have a kind of, you want to walk along a type of direction that's the minus gradient direction, but you have to project it to this tangent space. Don't go too far away from the feasible set. Okay, so this is the idea, and this is the optimality condition that we are able to show. And just to motivate this definition, we can look at a convex set. So let's assume that these constraints H and G, they form a convex set. And in that case, if you can characterize a solution, x star, by looking at this projected gradient. If this projected gradient is zero, then you are at a solution and this is equivalent. So this is the set omega, it's a convex set. And if the gradient, if minus the gradient of the objective function points this way, x1 is a solution. So if I compute this projection, x1 minus the gradient, it's this vector here. And if I project in omega, I go back to x1. Okay, so this is zero. And if I'm not at a solution, if I project, I don't go to, this is not zero. The projection minus the point is not zero. So if the set is convex like this, this condition makes sense. If the set's not convex, you have to linearize these constraints in order to be able to project on it. So as I mentioned, the idea to define the general condition for when we have inequality constraints is by looking at this set, omega k. This is the set that we want to linearize. So at an iteration, I have a point where I improve the feasibility to some value h of xk and some value g of xk. And in the next iteration, I want to keep this same value. So I want to look at the point z such that h of z is the same as before. And for the g's, I have this something like this. If at xk, gj of xk was feasible, my z's should remain feasible. If at xk, gj was infeasible, gj was greater than 0, gj of xk is greater than 0, the gj's of z's should be at least this value. So I should not lose the feasibility that I got at xk with regard to inequalities. So what we do here, we linearize this set. Instead of writing h of z, we look at the first order approximation of this h of z in around xk. So we get, if I plug this approximation here, you have an h of xk that will cancel here, I will get this. And this is the same. Gj of z, I can write it like this, and this inequality, I can write it like this. So this is the set where we want to project. Okay, so, and this is the general set tk here that defines the AGP condition for a general inequality and inequality constraint problem. Okay, so there are some other conditions. They are important for some other classes of problems. So assume that you have an algorithm that generates a sequence xk that always belongs to some convex set C. Okay, so for example, the external penalty method, we can define it in such a way that we can separate some constraints, this omega bar, and the iterates will always be feasible for this set omega bar. Your subproblems were built in such a way that you minimize another function, but these constraints should always be fulfilled. So if this forms a convex set, you can form this other kind of optimality condition called the convex AGP, where you project in the intersection of T and this convex set. And the sequence xk is always inside the set C. Or if you have, if you can separate the linear constraints, and your algorithm generates sequence inside this linear set, and you project in this intersection now. Okay, so these are two different optimality conditions. And this is done in particular in the solver Augin-Kahn that I mentioned for the Augmented Lagrangian. You always have box constraints. So your constraints, your variables are always between two values. And you have always inequalities of this form L less or equal X, L less or equal U. So your iterates always belongs to this box, so you have something like this. And for inexact restoration methods, you also have something like this. And when we were studying this kind of thing, we thought every condition, every possible sequential optimality condition that we could define, we thought that they were all the same. Okay, so the approximate KKT condition and the AGP condition, we thought it was the same. And if we separate a linear constraint, well, we thought this was the same also. But it's not the case. So we have we can prove some implication, but we have counterexamples for the other implications. So we see that if I have an algorithm that generates AGP points, these points will also be approximate KKT points. And if I have a local minimizer, they will be AGP points, but the set of AGP points is smaller than the set of AKKT points. So they give better optimality conditions. Okay, so you want something like that. if you look at this implication here, it says something like this. I have the set of local solutions, and I have the set of points that are fulfill this necessary optimality condition, something like here. So this shows that this set may be the AGP, and this larger set may be the AKKT points. Okay, so in terms of optimality condition, we want to define something that captures as much as possible only local solutions. I don't want points here that fulfills this condition but are not local solutions. So if this is, I want to build this condition as tight as possible to a local solution. And I don't want this to be outside I don't want to have local solutions that are not points of this class. So I want something like this, and this proves that we have a winner here. The linear AGP condition is better than the other ones. Okay, so if you have an algorithm, maybe it's a good idea to keep linear constraints always feasible. So you will probably generate conditions of this kind that are better than the other ones.
Do you know any kind of result in which you get an idea? So you had this picture with the three sets. Any kind of result, or I don't know, how could that be to know, let's say, the relative areas of the different sets? So we have a set of solutions. We know that there are some other solutions which will be identified by the algorithms, but which are not good. And I would like to know whether I have typically, in a typical problem, much more local solutions than non-regular solutions that might be identified by the algorithms. So if the local solutions, the set of local solutions is much bigger, and I'm just removing measure zero points, I wouldn't be so worried. Do you have any idea about that?
You mean something like if you want to measure this area here, this error, okay. For this kind of conditions, no, but I know something about if you generate randomly a problem, it will typically fulfill linear independence constraint qualification. So there is a result that says, well, the set of problems that does not fulfill has measure zero, something like that. So, but this is kind of misleading because in some applications you always have a pathological case. So if you look randomly, okay, this is not typical of what kind of problem that appears in practice. Okay, so and this lower part of the picture, this is showing that, well, in fact, this approximate KKT condition is at least as good as this other type of condition. So this is what is typically used. So let me go back to my drawing here. We have something like this. Okay, if you have a local solution and you have a constraint qualification, you get a KKT point. So so you can't say that KKT is necessary optimality condition. It is not. If you have a necessary optimality condition, is anything that holds for every local solution. So KKT does not hold for every local solution of any problem. You must look only at problems with this. So if you want to compare optimality conditions of this kind with optimality condition of this kind, I can simply put implication. I can put this condition to the other side. So I can write it like this. Local solution implies KKT or not CQ. Okay, so this is logically equivalent to writing the condition in the other form. So if you look at this, this is an optimality condition. And this I can compare with my type of optimality condition. So what we can prove, in fact we have proven this here. AKKT implies KKT or not in independence or Mangasarian from orbits. So in fact we can do this for this other constraint qualification, but if you look at this implication, you see that optimality conditions that of this kind are better than optimality conditions of this kind. So if you have an algorithm that says that under this constraint qualification I have a KKT point, and if I have an algorithm that says I generate approximate KKT points, mine algorithm is better. Okay, it's at least as good as yours. Okay, so continuing with this algorithm discussion, I should show you an example where this approximate KKT condition is not so good. Okay, so let's look at this problem in two variables and two constraints. So I want to minimize x2 minus 2 squared over 2, subject to this constraint. x1 equal to 0 and x1 times x2 is equal to 0. So this kind of constraint is really hard to solve. It's a type of complementarity constraint. It typically says that either x1 is 0 or x2 is 0. So this is hard to solve, and our optimality condition in fact fails for this type of problem. So let's see the solution here. So the constraint set simply says that x1 is 0, and this is redundant, it says nothing. And so the global solution to this problem is x1 0, x2 equal to 2. Okay? So, but if I can check that this point, x star of this form epsilon 1, it fulfills the approximate KKT condition. First thing is that it is almost feasible. So x1, if I take epsilon sufficiently small, my test for feasibility will be satisfied. Epsilon will be close to 0. And this product, x1 times x2, will be epsilon also, and this will be close to 0, and so it's almost feasible. And if I check the Lagrange condition, this will hold also. So I can take here x2 equal to 1, so this is minus 1. And if I plug here these values of lambda, 1 over epsilon, and lambda minus 1 over epsilon, I think when I checked this last night, I think the sign was changed here. So lambda 1 should be minus 1 over epsilon, and lambda 2 is 1 over epsilon. So you can check this, and this holds. So, okay, so this is, but this point is not good for me. The point epsilon 1, I don't care for that point. This is not a local solution. So, but the approximate KKT condition holds. Okay, so there is another paper that tries to address this issue. So it defines this type of complementarity, approximate KKT condition, and it simply replaces the tests of complementarity by this one. So remember I said that the complementarity was something like if the GJs of xk was less than minus epsilon, then the multiplier should be 0. So it turns out that this is too strict, and you can use something like that. So you can measure complementarity using the product of the multipliers mu, the approximation mu k, and the approximation gj of xk. If the product goes to 0, this is a good measure for complementarity. And in fact here you have a complementarity for equality constraints also, which is not usual. But in order to prove that this is an optimality condition, you need a complementarity also for the equality constraints. And this is very weird. When we saw this for the first time, we thought that something should be wrong, but it turns out that it's okay. And so we have an optimality condition that it's not so similar to the KKT condition because of this complementarity, but it's okay. And we also have an algorithm that generates sequence of this kind. So this is what we can prove. Every local minimizer satisfies this condition. This is a stronger condition than the linear AGP. So this is the stronger one that we know. And okay, so it's important to associate this condition, this kind of sequential condition, to an algorithm. That you must be able to generate and to build an algorithm that generates sequence whose limit points fulfill this condition. And this is the case for our implementation of the Augmented Lagrangian. It generates points under a very reasonable condition on each constraint. So it's not a constraint qualification, it's a condition on the function. It's something as sufficiently differentiable. You must have a Taylor expansion for large order. So it's a very reasonable assumption on optimization. So this is what we know. We don't know if other algorithms generate this kind of sequence. We only know this, our algorithm generates it. Okay, so maybe I should talk about this slide. We have used this idea also when the solver does not generate an approximation for the Lagrangian multipliers. So the Augmented Lagrangian does that, and many other solvers generate this approximation, but maybe you can use this idea to define stopping criteria when a solver does not provide you an approximation for the Lagrangian multipliers. And we have done this to genetic algorithm implementation. So it's an heuristic for global optimization, and we were able to define this stopping criteria for this problem. So, but in fact, you can do this in general for any solver that does not generate Lagrangian multipliers approximation. What we do is at each step where your iterate is close to feasibility, you try to define the lambdas and the mu's in this way. Okay, so you solve this problem, you minimize, your variable here is lambda and mu, and you minimize this norm squared of the gradient of the Lagrangian. And you put here, your sum here is made only on the approximate active set. So you can measure this like this. You can fix this tolerance for complementarity. And if your iterate xk is sufficiently close to being active, so your multiplier should be 0. If your constraint is inactive, your multiplier should be 0. So you should only add here the constraints that are close to being active. So if this is close to being active, you add this set, this index j here, and this should be a gj here. Okay, this is age. So you can solve this problem to define the lambda and the mu's. And it turns out that this is an easy problem. This is a least squares problem with non-negative variables. Okay, so you simply solve this least squares problem. It's easy because xk is fixed here. You know xk, and you simply want to compute lambda and mu. So this function is linear here in lambda and mu. And when you compute squares, well, you have a linear least squares problem. Okay, so and constraint you can simply remove. you can look a priori which of these constraints fulfill, which of these constraints are in this set. You can build this set before solving the problem, and you can then compute this objective function. So what we proved here, that if the sequence xk is converging to a kkt point, and if you take this epsilon sufficiently small, then this epsilon k that you compute here, this objective function, is going to 0. And under this constraint qualification, we can prove that limit points of sequence of multipliers are in fact Lagrange multipliers. So when we first saw this, there were some people using our conditions in this framework, so they didn't have any theorem that proved that this was reasonable. So they simply implemented something like this, and they said, well, genetic algorithms are really good because even without using the objective function, the gradients, I'm able to compute something such that this goes to 0. So, well, we proved that this is always the case. It's not a property of the genetic algorithm, and the sequence of multipliers converges also. So you can use this.
Excuse me, so suppose that I have an algorithm that just generates, I don't know, maybe I'm doing Monte Carlo and I'm just generating random points in the feasible set. Would it still make sense to take this as a stopping criterion? Just at some point I have a point in my sequence of randomly generated points that gets an epsilon k very close to 0. Would that still tell me that I'm probably close to a point that will satisfy the KKT conditions, or not?
I didn't get quite your question.
So I'm just...
You're using Monte Carlo?
So I'm just taking random points.
Random points?
Let's say they are feasible, and I just want to use your stopping criterion. So the sequence will not converge because I'm just taking points randomly, but still I want to use, if at some point I solve this and I get epsilon k being very small, is that a good indication for that point that I was lucky?
Yeah. You don't need to have this convergent sequence. If you have a grid of points, you can use this and stop your algorithm. The difficulty here, or the criticism that we get for this work, which is, I think it's valid, is if you are using Monte Carlo, if you are using genetic algorithm, you probably don't have derivatives of the function. If you had derivatives, you would be doing something else. Yeah, so, okay, this is a valid point. So I want to comment first thing, if I have a KKT point, X star is a KKT point, in fact you can use any sequence to check that this limit is an approximate KKT point. So if I choose any convergent sequence, xk convergent to X star, it can be generated by anything, a genetic algorithm or any other thing. You can compute the Lagrangian multipliers, and in fact you can use the true Lagrangian multipliers to check that the gradient of the Lagrangian is going to 0. So you can check that this X star is an approximate KKT point, no matter how you are converging to the sequence. So the picture is a little bit different when we don't have a KKT point. So when X star is not a KKT point, what can we say about this approximate KKT sequence? So let's look at a very simple problem. So we have to minimize x subject to x squared is less than or equal to 0. So there is only one feasible point, it's 0, and it's the global solution. So let's take a sequence, xk converging to 0, and let's look at the gradient of the Lagrangian. So it's the gradient of the function, that is 1, at xk, it's always 1, and this is k, the gradient of the multiplier times the gradient of the constraint. So we see that this constraint is active at the solution, so I should consider this constraint at the Lagrangian, and this gradient is 2xk. So if I look at this, and I want this to go to zero, and remember that mu k is always non-negative, I must have xk less than or equal to 0, so that this will hold. So this, if this is 1, this must be negative, such that this sum adds up to 0. So we see here that the approximate KKT points for this problem are only, you will only be able to check approximate KKT points if your algorithm converges to the solution coming from the left side. If your algorithm comes from the right side, you simply won't be able to check approximate KKT points. So we want to understand some more general property of this approximate KKT sequence, and we don't know it yet. It's an open problem to study this sequence when the limit is not a KKT point. Okay, so considering this same simple problem, now with the equality constraints, but it's as easy as the previous one. And I want to study what a well-known algorithm will do here. So the algorithm is the following. I will look at the KKT conditions for this problem. So it is feasibility, x squared should be 0, and this is optimality, so the Lagrange condition. 1 plus 2x lambda should be 0. And this is infeasible, okay? You won't be able to solve this. So when x squared is 0, x should be 0, and you won't be able to find lambda with this that fulfills this. So, but I want to know what the algorithm will do. So the algorithm is to solve this by the Newton method. So it's a system of two nonlinear equality constraints with two variables. I can compute the Newton direction. So the Newton direction, simply compute here the matrix of derivatives. So I compute derivatives here with respect to x and lambda, and derivatives here with respect to x and lambda. I get this matrix. So when I solve this, the derivative times the direction should be minus the function. This is the Newton method. Okay, so then I update my iterate. I have xk. I add this direction dx, and I have lambda k, my approximation to the multiplier lambda. I add this direction d lambda. Okay, so we see that xk in fact converges to the solution, x star. Lambda k is a divergent sequence, it goes to infinity, that's no problem. But what's not good is that the gradient of the Lagrangian is not going to 0. It's going to 1/3. So something went wrong here. This problem does not fulfill KKT condition. I used an algorithm, and it generated the wrong sequence. Okay? Because it's interesting that the AKKT condition, the approximate KKT condition, is an optimality condition. No matter how weird your problem is, you are always able to find sequence xk and lambda k such that everything goes to 0 smoothly. So why this Newton method is not finding this condition? So the Newton method is not working fine here, or our condition is not fine. But at least for this simple problem, with so we have only one inequality constraint and only one variable. For this case, we understand what the Newton method is doing. We are able to prove this result. Xk converges to a feasible point. Xk converges to x star. if xk converges to x star, then this is feasible, and the Lagrange condition converges to this value. It's not 0 in general. This value is something like this. It depends on how is the derivatives of the constraint at the solution x star. So if you have a point where the derivative is non-zero, so the difficulty here, the KKT condition does not hold because linear independence does not hold at the solution. The solution is 0, and if I compute the derivative, it is 0. So it's not a linear independent vector. So, for one variable on one constraint, this is the only difficulty. The derivative is non-zero. It is 0. So when the derivative is non-zero, okay, you in fact get 0. Okay, you will converge to a point, you won't have problem with the Newton method. The point will be a KKT point, and the Newton method will generate the right sequence. This will converge to 0. But if the first derivative of the constraint is 0, and the second one is non-zero, you will converge to 1/3. 1/3 times the derivative of f. In our case, it was 1. So if you have other function, you will converge to this, and you can compute. You have a general formula for which value this will converge. So to converge to something, if the third derivative is non-zero, you converge to 7/19. So you generate this sequence. It is tending to e minus 2 over e minus 1, approximate 0.42. So okay, this is the only case that we know something. We don't know anything else when we have more constraints or inequality constraints or more variables. Okay, but what it is interesting is that even when the solution is not the KKT point, it is an approximate KKT point. So you must be able to modify an algorithm such that it finds an approximate KKT sequence. So for this method, with this simple constraint, this paper that does this job, it in fact does that. It modifies slightly the method such that it always generates an approximate KKT sequence. Okay, so but there is this open question, this general question: how to tune a method such that it always finds this approximate KKT sequence that always exists. And this is important because practitioners are not interested in KKT points. They want solutions, they want minimizers, so you shouldn't look only at KKT points. So continuing with this discussion, there is this general discussion here. In optimization, you are trying to find the lowest possible value of a real function f over some domain. You are not looking for KKT points. So, and roughly speaking, you are looking for a global optimization. So you are not the practitioner are not even interested in local optimum. So they need global optimization. But this is too hard. Okay. And to have an idea of why this is too hard, if you want to find the global solution, so assume that you have an algorithm that is converging to the global solution. Okay. So if this is a reasonable algorithm, there should be some region of the space that you didn't look. Okay, so assume there is a very small ball in some region that your algorithm never looked at this region. So you are able to modify your function such that in that region you have now the global solution. So you can use other function that has the global minimum inside that region that your algorithm never looked. So since your algorithm is it's making decisions based on local information. When you run the algorithm for this new function, it will converge to the same point. So it will not converge to the global solution unless you look in a dense set of your constraint set. So this is why global optimization is so hard. So we don't do this. What we do is we rely on this, what we call affordable algorithms, that we can't guarantee global optimization, not even local. In general, you will have a point satisfying a necessary optimality condition. But the advantage of this is that it runs in a reasonable time. Okay, so that's why we call this an affordable algorithm. So there's some problem that arise with this. So assume that you have a solver A, and you are very strict with respect to infeasibility. You have a tolerance of 10 to the minus 10 tolerance for infeasibility. So you are very strict, and you run your solver, and you are smoothly converging to a point that satisfies the approximate KKT condition up to some tolerance, and the objective function is very low, is unexpectedly low. So you are very happy, of course, but when you show to your engineer, he says, well, this solution is completely wrong. This can't be the case. So this is the good case. The bad case is when the engineer does not realize that you are doing something wrong. Okay, so the reason for this is that you have a new conditioning of the constraints. So the tolerance 10 to the minus 10 is not enough to guarantee that your point is close to the feasible set. So there is an example here from PDE constraint optimization. So I have to minimize some functions subject to partial differential equation. So what we can do in practice, we discretize this PDE, and you may have something like this. So you have n nodes, and you have the value of x0, the boundary conditions on the function, and xn plus 1, this is 1, and this is how your PDE says that this should evolve. So if every xi is the average of their neighbors. So the solution here, of course, is the constant vector xi is equal to 1. Okay, so, but if you are trying to minimize this function subject to this constraint, what an algorithm may return is something like this. Okay, this is every I from 1 to n, and this is the value of xi. The solution should be a straight line here, but it gives this value with very low objective function. It's lower than you would expect, but it's not feasible. The difficulty here, you have the norm of the infeasibility is small, 10 to the minus 6, but for this application, this is not small enough. Okay, so if we look at three neighbors here, three points here, neighbors, this condition will be very well fulfilled with a small tolerance, but even when you add it up, you still have a small tolerance, but in practice, this is not good enough. So what should we do? I don't know. This problem is really hard. It's very challenging to solve PDE constraint optimization, but I don't know what we could do here, but that is some kind of problem that we need to focus if you are going to apply these ideas in practice. So another important thing that we are not able to prove that a method always obtains feasible points. Okay, so we saw in the previous this external penalty method. In fact, we proved that it converges to a stationary point or to a minimizer of the stationary of the infeasibility measure. Okay, so assume that you have a problem where there is only one stationary point of the infeasibility measure. Okay? In general, that's what an algorithm will do. If you remember the external penalty method, you are always looking for the global solution at each step, and then you are able to find a feasible point if it exists. But in an affordable algorithm, you can't look for the global solution. So what you will be able to prove is that the limit points are stationary points for this problem of minimizing the infeasibility. Okay, so assume you have a problem with only one stationary point for the infeasibility measure. Your affordable algorithm will converge to this point. Now you can do the same trick by changing the problem in a region that your algorithm never visited, and you can make the problem feasible in that region. If you run your algorithm again, you will converge to the infeasible point that is the minimizer of the infeasibility, and even though a feasible point exists, you will not find it. Okay, so this is what is written here. Okay, so this is another idea is that even if you are in practice you want to find the global minimum, so but you could think that okay, these affordable algorithms, they are useless. Okay, you want the global minimizer, you are only finding KKT points. I don't care for KKT points. So what should we do? So what we argue is that if you want a global minimum, what you can do, you can solve your problem many times. You start with different starting points, and you are going to converge to a stationary point. But if you start close enough to the global solution, you expect to converge to this global solution. So, but sometimes, usually, the local optimization community and the global optimization community, they do not talk to each other. We do our local methods and they do their global methods. And okay, so let's compare two algorithms. So algorithm A is a local method. It finds a stationary point, KKT, very good, the theory works fine, it's feasible, but the objective function value is terrible. It's 999, but you can do this in 1 second. So you can give this back to the engineer. Okay, this is your solution. The other algorithm, it finds a feasible point. Maybe it's not even stationary, not a global solution, but the objective value is 17. Okay, and he takes 15 minutes to do this. Which algorithm is better? Okay, probably the engineer will stay with the algorithm because he wants the global mean. He wants the lowest possible value of the objective function that you can find. He doesn't care for stationarity. So the message here is that modern affordable algorithms should in fact incorporate this idea to make their algorithms better. So see, if I had algorithm A should say something like this. Well, but your algorithm uses 15 minutes. If I had this time, I could run my algorithm many times and I would find a point better than yours. Okay, so the message is just do it then. Okay, so you have to be, if you want to build a solver that is good enough to be applied in practice, you should incorporate this heuristic or meta-heuristic that are looking for problems with looking for the global solution. And in fact, Augen-Kahn, our solver for Augmented Lagrangian, it does something like this. Its convergence theory is okay, but it incorporates some other procedures to try to find the global solution, even if there is not an elegant convergence theory in this case. And it's done because this corresponds better to what practical applications need. Okay, so this is it for today. I have here some reference. So the first one is the paper about the approximate KKT condition. So we have the definition of this condition and this other LAGP, convex AGP, it's all there. The second one is the definition of the AGP, optimality condition, so it's a little bit older. This third one is about the complementarity, approximate KKT condition, and prove that the augmented Lagrangian generates this kind of sequence. This one is about the implementation on genetic algorithm when Lagrange multipliers are not available. And this one is about that Newton method, that theorems when you have only one constraint and one variables. And this is in this paper. Okay, that's it. Thanks.